So this is not a command to do something. I think a lot of students see that as a command to do something. Take something and plug numbers into it. Instead, what is that? It's not a command for you to do something. It represents a value. It represents a number. Now, if you want to get that value, yes, you're going to plug in a 3 and a 5, and that will give you. But just on its own, just sitting there without doing anything, it represents something important, right? It represents some value. What value is it? He said it's the rate of change of this function f in the y direction from the point x equals 3, y equals 5. Okay, so it's the rate of change of the function f with respect to y at the point x equals 3, y equals 5. All right, so let's find that. Where is x equals 3, y equals 5? Here's x equals 3, y equals 5 is here. So is it 12? What is 12? That's f of 3, 5, right? That's just the value of the function. That's the height, the z height, the value of z when x is 3 and y is 5. What do we want? We want the rate of change. So now we know we've talked about 2 rates of change, right? 2 rates of change. There's a rate of change in the direction of x and the rate of change in the direction of y. So if we want to look at the rate of change in the direction of y, what do we have to do first? Okay, good. That's what you should be thinking. We have to hold x constant. So holding x constant means holding x at 3. We're only going to look along this trace for constant x of 3. And we're going to say, what's the rate of change of y? What's the rate of change with respect to y? So, what is that essentially? The rate of change with respect to y is? Right. It's going to be the change in the function over the change in y. Remember, given any change in y, the change in f will be equal to what? That rate times whatever little change in y you picked. That's our meaning for rate of change. Given a little change in your independent variable, the change in the dependent variable, which is f or z, dz, you could say, is that rate times whatever little change you picked. Therefore, the rate of change of y is the change in z, or the change in f, over the change in y. So we're going to use the chart to give us a change in z and a change in y. So what can we do here? So it looks like whether we go up or down in y, it doesn't matter. So we can go up this way, or we can go down this way. It looks like we're getting the same change in z, whether we go positive y or negative y. So that makes it easy. We can just choose either one. Last time I suggested that if it's different going in positive y direction versus negative y, if you wanted a more accurate result, you could average the 2, right? You could average the 2. But if we're just estimating, you can just pick one, average the 2. So what is the change in y that we see there? 2. You're going from 5 up to 7 right there. So that is my dy is positive 2. And when I make that change in y, what's my resulting change in z? Also 2. Okay, it's not that easy for everybody. So, all right. So here you're at the contour line for z equals 12, and we're moving up to the contour line for z equals 14. So when you make that change in y of 2, the change in z is also 2. So what's the rate of change with respect to y, or an estimate for it? Positive 1. Positive 1. It'd be dz divided by dy. Or df divided by dy, whatever, either way. So that'd be 1 over 1. Go the other way, it looks like you get the same thing. You're going to you could go negative 2 in y. It looks like you also go negative 2 in z. So you get the same thing. -2 over -2 is 1. Questions on that? Those doesn't make sense. The contour lines give us our change in z, and we can look at changes in x horizontally and changes in y vertically, and then we can just estimate what that rate of change is. Okay, the number 1 in the written. So you needed to show that the rate of change of velocity was equal to, I don't remember, r prime. Oh, there's no, it's dot product, right? So there's none of this, right? I don't remember what it is. Squared or something? No? Just like that? Okay. By the way, you'll happen to know that on exam 2, you'll have several formulas given to you on the cover. Okay? There's lots of formulas here, and I'm not interested in memorizing. As you can see, I didn't even know what this was. Much more interested in ideas and your ability, your understanding of things. Okay, so how do we do this? Well, we're gonna get what is v, and we're gonna take the derivative of that. Right? So what is v? V is the speed or the magnitude of r prime. Right? So if you had the r prime vector, that would be like velocity. So then if you take the magnitude of it, you get a scalar function, a real valued function, that would be this. So what is that? The magnitude of r prime would be basically f prime of x, g prime of x, h prime of x, all divided by the square root of each of those things squared, right? Yes, I was thinking this is way too hard. It's just the magnitude of it. It's just this. Thank you. Yeah, I knew something was wrong there. That's better. Okay, so this is v. Okay, and what do we need to? We need to show that these are equal, so we need to take the derivative with respect to x, right? So the derivative with respect to x, I'm just do the first step. So I assume this side is easy, right? This working out this side's easy. So we need the derivative of this with respect to x. Well, what do we got? We've got square root of a function, and each of those little functions is squared. So we've got a lot of chain rule going on here. So we got to know our chain rule. So square root, derivative of square root is 1 over 2 square root. So 1 over 2, we know it's the same thing there. But then times the rate of change of the inside. Okay, so we need the rate of change of what's inside. So now we come to this first thing. It's a sum, so we'll do each rate of change individually. And so what is the rate of change of that? So that's chain rule, right? So it's going to be 2 times f prime of x to the first times the rate of change of the inside, f double prime. And all three will look like that. And then I think from there, you can kind of work on this a little while and see that, and just meet halfway. So that's really maybe the hardest step. And then once you evaluate that, you can kind of see how it should look very much like that, or maybe you're one step away or something like that. So the real, I guess that would be the tricky step, the one I just did, taking the derivative of the magnitude of r prime. This is the magnitude of r prime. The derivative is going to be chain rule, 1 over 2 square root times the rate of change of the inside, which is a sum, and then each one of those is a little chain rule problem. 2 times that to the first, times the rate of change of the inside, etc. Same thing for G, same thing for H. And I think that will look pretty similar, 1 or 2 steps away from what you get when you work that out. Does that, those who've rested this, does that help? Okay, very good. So I want you to work on something here. I want you to the right function here. How many variables is this in? Or if we're thinking about sketching the surface, how many variables do we have? No, not 2. This is z, right? Right? The dependent variable f of x, y, if we put that in R3, that would be z. So we have all 3 variables, right? In terms of sketching a surface is what I mean. Yes, this is a multivariable function of 2 variables, right? In terms of independent. But in terms of sketching a surface, we have all 3 variables, z, x, and y. So we can think of this like z minus 4 equals negative x squared minus 2 minus y squared over 4. And that is what? So we have linear and quadratic and quadratic. Remember what that is? That's a paraboloid, right? It's a paraboloid, and it's elliptical or circular? Elliptical. It's elliptical paraboloid. Opening. In the negative what? Negative, opening on the negative z-axis. Opening downward, okay? And how do you know that? Because you got z equals not x squared plus y squared, but minus x squared minus y squared. So this is just a variation on our, just a basic paraboloid, z equals x squared plus y squared. It opens down and it's shifted up 4, and it's elliptical. Okay, so if you never learned those, learn the surfaces, cones, ellipsoids, paraboloids, spheres, make sure you learn them. Make sure you learn them, and you can sketch them, and you can identify them, okay? That was right before the first exam, but we're gonna have them all semester, okay? So all this stuff that we're doing, we're laying the groundwork for the hard stuff. And so when we get to the hard stuff, you can't be tripped up with the easy stuff because it's all involved, okay? It's all involved. So, yeah, so when we get to vector calc in October, we start doing vector calc. It's hard, okay? And like I said, if we don't know basic space curves, basic surfaces, just all the basics of R3 and vectors, then we'll be dead off the starting line, okay? All right, so now here I'm showing just the part of this that's in the first octant, right? Positive x, positive y, and positive z. So this is x, and this is y, and this is z, and that's just for my purposes. But when you sketch it, you kind of sketch the whole thing, right? You sketch the whole thing, but just for what we're doing today, what I'm showing is just the first octant, all positive coordinates. Okay, then I'm also showing the point for xy 2, 2. And what is the corresponding z value when x and y is when they're each 2? So here's the point 2, 2, 0. And that lies in the xy plane. So what is the actual coordinates of the point on the surface when x is 2 and y is 2? Some people are saying 1. That's correct. So this is the point 2, 2, 1. Or f of 2, 2. You should see that that represents the z coordinate on the surface for x is 2 and y is 2. and that is equal to 1. So that's the point 2, 2, 1. Okay, so I'm going to show you a line. And that line is tangent to the surface at the point 2, 2, 1. And you see that it's also parallel to the xz plane. You see that? It's parallel to the xz plane. So what recent idea does that line relate to? What's that?
Partial derivative.
Which partial derivative? So what does that relate to?
Why? Wait, it's going. I can't see. It's spinning too fast. Why?
So is this the have to do with the partial derivative with respect to x or the partial derivative with respect to y? Yeah, we're keeping y constant. It's like if you were there and you took a step in the x direction, what would your rate of change be? So that would be right along that line, right? Can you find the equation of that line? All right, so I sense there's a great struggle here, so we're going to make this a homework question, so you can go have time to research it rather than me tell you. But you got to remember these things. So figure out what's the general form of an equation of a line in space. What do you need then to write the equation of this line, and how are you gonna get what you need? Okay. So we'll just make it homework. We'll just put it on hold. Okay. All right. So we said that there was. What did we say? We said that there was rate of change. And that you can kind of see that's the rate of change of the surface in the x direction. And then we said that there was a rate of change in the y direction. You can kind of see it with the red one, right? It should look red to you. There we go. So there's the black one is the rate of change. It's representing or showing a rate of change in the x direction. And then the red one kind of coming at you now is showing rate of change in the y direction. So now on this surface, there are two rates of change, right? Two rates of change. Is that right? What's that? Why? Why do you say there's infinite? So when we talk about the rate of change in the direction of x and the direction of y, those are very specific directions, right? And so how is it that there's an infinite number of really rates of change? Okay. No, at this one point. How many rates of change exist at that one point on the surface? Right, so x is one specific direction of any direction, and y is one specific direction of any direction. Okay? And so really, if we think about, so here's this point down below, so I'll turn these off. So at this point down below, we could think of putting a circle down there. And we could think of any direction. And if we chose a direction, we could choose a direction, and there'd be, in that direction, there would be a corresponding rate of change on the surface at that point. Do you see that? So I can kind of show that this way. So now I have a vector that's as we change the direction is showing the rate of change. So here I'm pointing in the y direction. So now that vector is there. Right there. So now that vector, the blue one, is pointing in the direction of positive y. So now what is the rate of change in the direction of the black vector? What is that rate of change? That's one we know already, right? What do we call that? Partial derivative with respect to y. That black one is representing or showing the partial derivative with respect to y because I've chosen the direction to be the positive y direction. If I choose that direction to be positive x, then that black vector is showing that what I showed you before, the partial derivative with respect to x. But there's all these other ones, right? So I've got all these other directions I could pick. So how can I, given a direction, and so what's that direction going to be given? That the direction is going to be in terms of our angle theta, and that's our standard trig angle, right? Because it's the angle swept from the positive x-axis, right? Like, so if I'm standing over here, looking down, I'm looking at my conventional xy coordinate, right? X is to the right, y is up, and there's my standard angle from the positive x-axis. Do you see that? That's the same trig angle you've been working with since pre-calculus. Swept counterclockwise from the positive x-axis. So given an angle theta, what's the rate of change of the surface in that direction at the given point? That's what's called the directional derivative. That's what's called the directional derivative. So it's the rate of change in the direction theta of our surface or of our function at that given point. So does the setup make sense? So that kind of begs some questions. At what angle? Well, we haven't gotten to how to get the derivative, but it makes you think, like, okay, so what angle gives me the maximum derivative? Something back here, right? We get the maximum rate of change for some angle here in the third quadrant, right? The third quadrant between what? Pi and 3 pi over 2 for this particular surface is going to give me the greatest rate of change, right? Where's the rate of change? Do you agree that somewhere the rate of change is 0? So imagine you're standing on a mountain, on the side of a mountain. There's always going to be a direction you can walk without changing your elevation, right? Kind of like around the mountain. So somewhere the rate of change is 0. What direction is that? What direction theta is that? These are all questions we want to ask. But first we got to figure out, given theta, how do we get the rate of change of the surface in that direction? Where'd it go? Good. All right, so let's do that. Directional derivative. We want the derivative in the direction of theta, right? We want the rate of change of our function, the derivative in the direction of theta, no matter what theta is. Okay, so we're going to, let's go back to the picture and think about, if I just had a really small angle theta, what would the rate of change be kind of like? What would it be really close to? Partial with respect to x, right? And as I increase theta up until pi over 2, what happens to that rate of change? It becomes more like partial with respect to y until I get to pi over 2, and then it is the partial with respect to y. So that kind of gives us a clue of what's going on. It's kind of, the rate of change is a weighted combination of the two partials. So those two partials are really important because we can kind of do a linear combination of those with the right weighting to get us the derivative in the direction of theta. So if it's really close, for low theta, it's really close to the partial with respect to x. And for, say, theta is close to pi over 2, our rate of change is close to the partial with respect to y, then how should we weight these? Right, so we want, in terms of theta, right? In terms of theta, how should we weight these so that, say, when it's 0, we get all partial derivative with respect to x, when the angle is 0. When the angle is pi over 2, we get all partial with respect to y. And then as that angle increases from 0 to pi over 2, the weight shifts, right? The weight shifts from everything on partial of x to everything being on partial of y. So what is this a matter of with using theta? Yeah, so this is just, so f of x would be times cosine, and f of y would be times sine. And so let's see if it works. When theta is 0, do we get all partial derivative with respect to x? Right, sine is 0, so partial y goes away. And then when theta is pi over 2, we get all partial with respect to y, and no cosine of pi over 2 is 0. And then in between, we're going to get this, again, the shifting of weight from the value of the partial with respect to x to the value of the partial with respect to y. So this is actually it. This gives us, that formula will give us the directional derivative. We want to kind of mess around with that a little bit. So this is what we said. So look, notice we have product of fx cosine theta plus the product of fy sine theta. What thing have we seen so far that kind of has that form? Multiply, multiply, and add. What about vectors, right? So what about vectors had that kind of form? Multiply, multiply, add together. Dot product. So what would it be the dot product of? Write it down. What would this be the dot product of? What two vectors would this be the dot product of? What two original vectors? If you took the dot product, you'd get that. The first vector would be fx, comma, fy. Second would be cosine theta, sine theta, right? So this directional derivative is really a dot product. It's a dot product of this vector made up of our two partial derivatives. Those form the those are like the anchors from which we can get any rate of change in any direction. So you put those together in a vector, okay? And then what is cosine theta, sine theta? What vector is that? So what vector is it, right? What vector is it? So yeah, so cosine theta, sine theta, it gives us that circle, right? And so then the vector is what, just the vector pointing in the direction we want. So that vector is pointing, if this is theta, then that vector in the unit circle is cosine theta, sine theta. Okay, so that first vector, when you take the partial derivatives and make a vector out of them, is called the gradient vector. And the second vector that so gradient is use this del symbol, so you say del f. Del f is the gradient vector. It's the vector made up of the partial derivatives. And then cosine theta, sine theta is what? That's a unit vector, so we call it u, right? That's always has length 1. And so that u is the direction we're interested in finding the rate of change. So we started talking in terms of theta, and if you have theta, you can find u this way, cosine theta, sine theta. But really, if you just have the direction based on a vector, you don't need to know what theta is. You just need the unit vector in the direction you want. See? You're not going to every time be given a theta and figure out cosine theta, sine theta. You'll have information. It'll say, in this direction, 3, 5. Well, then theta's not really involved. You just find the unit vector in the direction 3, 5. You see? So it's not always going to be about theta. We start talking in terms of theta, but sometimes you'll say, in the direction, -6, 3.5. Well, then you need to find, if you're going to find u, then you just need to find the unitized version of that. Okay, so this is our notation for directional derivative. D sub u f x, okay? So it's only going to be f if your function named is f, right? If you're talking about the function g or h or some other name of the function, then you're going to put that name of the function in there. F is just our most commonly used generic name for a function. But if you have the function g, it's going to be d sub u g of x. If you have the function capital B, it's going to be d sub u capital D of x. Now, u is universal. We'll always use u to mean the unit vector in the direction we want. So this is a number, right? This is the rate of change of the function f at a given point in the direction of u. Lots going on there, right? It's the rate of change of the function f at a particular point in the direction of u. Okay, so if it's the dot product, then we have an alternate way to write that. What's the alternate way to write the directional derivative if it's a dot product? Remember? Okay, good. Yeah, so we're going to do, it's going to be the magnitude of del f, or the magnitude of the gradient vector, times the magnitude of u, times cosine. I want to use a different symbol. This isn't our theta, right? So theta is our standard trig angle. Now what's alpha? Alpha is not theta. How would we define alpha? Yaakov. Right, so it's going to be the angle between our chosen direction u and whatever the direction of the gradient is, right? So this gradient vector, we just stuck the partial derivatives into a vector. That's going to have a direction and magnitude, right? So whatever the direction of that gradient is, and whatever direction of u is, alpha is the angle between those two. So anything we can do with this now? Anything you notice? Magnitude of del f, magnitude of u. So, yeah, so what's the magnitude of u? Just 1, so that really goes away, right? Okay, so let's see here. Let's just practice a little bit before we go any further. So we'll just put the slide on hold and go back to our picture and practice a little bit. Any questions so far? So there's a lot of for the directional derivative, there's a lot of different things that you need to have the directional derivative. You need a particular point on the surface, right? Move from point to point, that's all going to change. So you pick a particular point. Then you have to pick a direction that you're going to go. That's that unit circle, right? And then based on the function and the point you chose on the function, the direction you chose to go, there's going to be a rate of change in that direction. And that's what that whole thing means, right? The rate of change in the direction of u at whatever point you're choosing on the function. So on the example that we're doing here, let's go back to the picture. let's do, so find the directional derivative, find the rate of change. At the given of f at 2, 2, 1 in the direction theta equals, let's say, 3 pi over 4. And then find the rate of change of f. So that's A, B, in the direction, say, 3, 1. So 2 exercises here. So given our surface that I gave you, and the same point, the point 2, 2, 1, find the rate of change of f in the direction of theta equals 3 pi over 4. So can you tell me where that would be if I tell me to stop? Here's 0, right? So where would 3 pi over 4 be? Did I miss it? Something like that? Let's see here. Is that it? Yeah. Okay. So, and what are you expecting for your answer there? Just in a very general prediction here. What do you expect for the direction derivative when theta is 3 pi over 4? You could just say anything, one thing, right away. What could you say? You know. Positive. It's going up, right? It's going up there. So if you go in that direction on this curve, you'd be heading uphill. Rate of change, you're expecting it to be positive. Okay? And then in the direction 3, 1. So now you don't need theta, but you're still going to use the same way to calculate it. But you need to figure out what u is if you're going in the direction of 3, 1. What direction is that? What direction is that? 3, 1. So where is that? First, second, third, or fourth quadrant? First. More in the direction of x or more in the direction of y? X. So maybe something like around here. This would be the direction of 3, 1. But to calculate the directional derivative, you need the unit vector version of that. Okay, go. You got 2 exercises. Okay, is there one of those you want me to talk about? B? Okay, so directional derivative is, so we're talking f at 2, 2. So that's how we would write this. This is what we want. And now u is our direction in the direction 3, 1. And we know, we know this is what? Del f dot u. So what did you find for the gradient? What's the gradient? -2. So this is particularly at 2, 2, right? So this gradient vector, we're going to use the actual values at the point 2, 2. So did you get -2, -1? And then dot, well, we need a unit vector in that direction. How do we make a unit vector in that direction? 3 over radical 10, 1 over radical 10. So no calculator, right? You just get an exact answer. This isn't about calculator. So -6 and -1, -7 over radical 10, right? Done. And does that agree with the picture? How does that agree with what we're looking at there? if we go in this direction, rate of change is, or we're heading down, right? We're heading down in that direction, and that at that rate. Meaning, given us any small change in this direction, remember this? This is what rate of change is all about. Given any small change now in this direction, what can we say? Well, finish the statement. Tell the person next to you. Given any small change in this direction, tell the person next to you. Finish it. Okay. Catherine, can you finish it for me? All right. Given any small change in the direction of 3, 1, what's true? Function will change that much. So that's not the whole thing. Sorry, I think you got it, but I only heard bits and pieces. So we start. Given any change in the direction of 3, 1 along the blue vector, conclusion. Almost. It's going to change that much? So what you said was, you had everything, but you said that z is going to change this much. It's not that z is going to change this much, but what? It's going to change. The amount that z will change will be this times whatever small change you picked in the direction of u. So dz equals -7 over radical 10 times, can I say du? I have no idea if that's good notation or not, but that's the idea, right? A little change in the direction of u will result in a change in z of -7 over radical 10 times that little change in u. That's what we mean by that rate of change. Okay, so I kind of brought up the question before. In what direction do we get maximum rate of change? So let's see what that looks like. In what direction do we get maximum rate of change? No, I'm just posing. I'm not asking you to answer. I'm just posing it. So we want to. So this comes back to this form of it, right? So I'm going to look at this now. So I'm asking, how do we maximize that? So how do we maximize del f cosine alpha? So do we have any say in the magnitude of del f? No, that's a constant, right? If we're at a given point, the magnitude of del f is fixed. So what can change? This. If I want to maximize this whole thing, what should I make cosine alpha? What's the biggest cosine alpha could be? 1, right? And if a cosine alpha is 1, then that implies that the value of the directional derivative is the magnitude of the gradient. So this isn't the direction, but this is just what is the biggest possible derivative we get, right? What is the biggest possible value of the directional derivative we get? Well, it ends up being the magnitude of the gradient. Because it would be when cosine of alpha is 1. That's the best we could do. And then that leaves us with the directional derivative just equals the magnitude of the gradient. Does that make sense? A few nods. So, in the example we're working on, what's the maximum possible value of all directional derivatives at the point 2, 2, 1? So if we were to go around in a circle, what's the maximum rate of change we're going to get? What is the maximum rate of change is what I'm asking. What's the maximum rate of change? I'm not asking for the direction of it. I'm asking for the maximum rate of change. What does it tell us? Magnitude of the gradient. And what's the magnitude of the gradient at 2, 2, 1? Square root of 5, right? Because the gradient is what, -2, -1? Magnitude of that is square root of 5. So of all the rates of change we could get going around, the biggest rate of change we're going to get is square root of 5. And then the next question is, in what direction does that occur? In what direction is it maximized? Again, it's when cosine of alpha equals 1. So what would alpha be? Cosine of alpha equals 1. What's the value of alpha to get cosine alpha to be 1? 0. So 0, okay? So what does that mean? Alpha equals 0, right? What was alpha? Alpha is the angle between these two vectors. Remember, we get to choose what u is. We get to choose what u is, and so we're going to choose u so that alpha is 0. So what direction of u do we choose? We get to choose u to be anything we want. And we're going to choose that so that the angle between u and the gradient is 0. Therefore, direction of the gradient. We're going to choose u to be in the direction of the gradient. That's going to give us an alpha of 0, and it's going to maximize, it's going to give us this maximum derivative. Okay? So, if cosine alpha equals 1, that means alpha is 0. That means choose u to be in the same direction as the gradient. So find that. What's the direction of the gradient? What's the direction of your gradient? Okay, anybody have a question before I go back to the picture? So really, this maximum, the maximum value and direction of the maximum directional derivative, it's all about the gradient, right? It's all about the gradient. This vector of partial derivatives. The magnitude of that vector of partial derivatives is the magnitude of the max directional derivative. The direction of the gradient is the direction of the maximum rate of change. So the direction is what? So we got -2, -1. Is that right? The magnitude is radical 5, and the direction is, so you could just say the direction is -2, -1. That's fine. Or you can unitize it. Doesn't matter, right? So let's take a look. So what is the direction? So the direction -2, -1 is this. I gotta turn all this stuff on. Okay, so the direction of the there we go. Okay. The direction there, that vector back there is the vector -2, -1. And if I line it up, I get the direction of max rate of change up towards the vertex of the peak, right? And notice what happens. Now I'm showing the contour plot over here. Notice what happens when I go point the vector in the direction of, so this is that same circle I had before down here, but now just looking in the contour plane. So the circle. What do you notice? What's the direction of max ascent? Can you see the contour lines? It's not pointing at the origin. Yep, it's orthogonal to the contour line. You see this? That the direction of max rate of change is orthogonal to your contour line. It's the most away from going, so if you walked along the contour line, how would your z be changing? It wouldn't change. So we want the most away from that, or 90 degrees away from that, a pi over 2 away from that. So if you were to walk along the contour line, your change in z would be 0. So we want the most contrast to that, which would be perpendicular to the contour line. So perpendicular to that contour line is going to give you the max rate of change, and then you can see it here, over here. Heading up as steep as it will go. That's in the third quadrant, in the direction of -2, -1. And what is that rate of change? What do we find that rate of change was? Radical 5. The magnitude of the gradient is that rate of change. Okay, and then I kind of mentioned it there. Orthogonal to that, then, is the direction of 0 rate of change, or alpha equals 90. If alpha is 90, we get the direction of 0 rate of change, and so that's only right there at that point, right there. So in the same tangent to the contour line gives you a directional derivative of 0. That corresponds to alpha equals pi over 2. So directional derivative equals 0. This is alpha equals 0. Directional derivative is max. And that's orthogonal to the contour line. How do you walk the steepest way up the mountain? You're going to walk orthogonal to contour lines. How are you going to stay at the same elevation? You're going to stay on contour lines. And those are always at 90, orthogonal to each other. Okay.